So what I normally do when we get further along in the book is kind of start with the later stuff and work backwards. But in this case, we need to make sure that everybody's on board with just the basic z-score problem. Because what two tweaks have we seen so far to that basic? What is a basic z-score problem? Well, when I say that, do you know what I mean by that? What does that mean? Can somebody tell me? I could, but I won't deal with that. Say again?
Is it the transfer from X to Z to
I love it. When I say little X to Z to percentage, that little thing I showed you guys, and sometimes you have to go backwards if they do a percentile actually. That's a classic z-score problem. What's the probability I get one person whose height is this, if you know the average height and the standard deviation, all that kind of stuff. What's that probability? And of course it also has to be normally distributed, whatever this stuff we're looking at is. You take that X score, you make it into a Z score, and you look at the percentage, right? And on the quiz, a few of you guys made the mistake, and this happens a lot. You calculate a Z score and you get something like 0.47, and then you say, okay, the answer is 47%. Yay. But what step did you skip? You didn't look up the percentage. That's just the Z score. That just tells you where you are. That doesn't tell you anything about the percentage of people on one side or the other side. It just tells you you're almost half a step up from the mean. That's all it tells you. And it would especially be weird if you got a 1.47 z-score and you're trying to say it's a 147% chance. That kind of freaks me out a little bit. I'm not sure what that means. Right? Something else too, if you get two z-scores, say you get a z-score of 2.1 and a z-score of -1, and I'll see this all the time. Somebody's next step is to do this. And then, so there's two things really wrong with this. One thing is that's bigger than 1. Okay, that's bad. That's trying to tell you, the math is saying, hey, I'm just math. You're the human, but listen to me. You made a freaking mistake. That's bigger than 1. Doesn't make any sense. Secondly, z-scores tell me where I am. If I subtract 2 z-scores, I am now somewhere else. Not in relation to what I want to know. Does that make sense? You never subtract 2 z-scores. It'll take you somewhere you're not supposed to be. You're not supposed to be up here at 3.1. You're supposed to be in between 2.1 and -1. You got to look those areas up. So a lot of you guys did the work okay, but then you didn't take that last step correctly. You didn't go get the probability. Let's see. What else happened on the quiz? Who just came in? Let me see. Josh. Who was that? All right. Oh. Three of us. Oh, is it? That's your good overall. All right. Let's see. I think that was the major problem, and then we all had some trouble with part B on number 2. So that's where I'm kind of leaning towards. You've got your basic z-score problem where they give you an x. They say, wow. They say the probability x greater than 48 or something. Then you get a z-score from the z-score formula, and then you look up a probability from the z-score chart. That's what I call a classic z-score problem. An untouched, basic z-score problem. Now, we've looked at 2 ways that kind of problem can change a little bit. Can somebody give me one of those ways that something might change in this recipe? What might change here? What would make something change?
Drawn as V instead of X.
I like it. So they take a sample and they ask a question about the sample mean, right? What's got to change then? So one tweak we can do One tweak. One tweak to the basic z-score problem. Is that they take a sample. Come on, Johnny. Of n things. The only thing that really changes it, the process doesn't change. It's just that this changes, right? You have to use this now. So that's one tweak we've seen. And I desperately want you to understand how that's awesome. The idea took forever for me to explain. Some of you guys still don't quite get it. It's your favorite section, section 6.4. And trust me, I understand. It's really, on my side, it's frustrating because it's really weird. And it takes a while to really get. The funky thing is, on the actual work side, barely anything happens. So in your brain, you're like, all right, wait a minute, it was so weird. Section 6.4 made no sense. But that's all I got to do? Yeah, that's all I got to do. That's all that comes out of all that concept is that one little change.
Do you have a key for the quizzes that's available?
Not available, no.
Okay.
Yeah, otherwise that whole corrections thing would be really
right.
moved. Yeah. Make corrections, and you can see the key. Yeah. But you can ask me anything about it on there. Yeah. What's the other tweak? So this is section 6.4.6.5. What's the second tweak we talked about?
Continuity correction.
Yeah, continuity correction. Now, I've only graded one set of Chapter 6 homework, I think, so far. And you got to be careful when you go into it. They have that whole section that's just continuity correction. If it's greater than 6, can you do the continuity correction? Now, carry that idea over. When you start doing the problems, make sure you're actually doing a continuity correction. Make sure the 6 becomes 6.5, or the 11 goes down to 10.5, or something. I mean, that's got to happen when you're using a binomial, but you want to, on top of that, use a normal distribution. That's the reason they had that whole section in there. Just make sure you are actually changing the number. So with this tweak, your x actually changes, up or down by 0.5. And that's really because it truly is kind of funky. It's just a bar. There's a 6, but the bar tells me it actually goes from 5.5 to 6.5. That idea is cool. Very simple idea. It really is. We've been talking about the sides of a bar since chapter 2. All right, so it's a very simple idea, and the actual tweak itself is simple if you let it be simple. Don't try to memorize it. So for example, if I had a question like that you had to use the nav on, and I want to know the probability that x is at least 11. You with me so far? How would you do the continuity correction for that? What could it be? What's the two sides here? 10.5? 11 or 11.5. And I want to shade which direction? Up, right? Greater than or equal to? So I want to shade up. And do I want to include this bar or not? So if I want to shade up, I can either shade from there or I can shade from there. I want to include the bar, so I don't want to do that. I want to do this. My continuity correction is make it 10.5. Then you make a z-score out of 10.5, not 11. Again, the process stays the same. It's just that you make a z-score out of the right x. Not the 11 you were given, but the 10.5. Why do we do that weird shit? Because we're trying to use a normal distribution for something that's not continuous. We have to correct for that. That's why that's there. And it makes that approximation better than it would have been. Now, the really big thing, I'll tell you honestly, this is the honest truth. We're not going to do this very often in this class. What really comes out of this section, which is kind of funny, what's really, really important here is when do you know it's normal? When is binomial normal enough? When is that going to happen? When is it normal enough? What do we have to check? I say that like that because it's normally a trigger. What do you check in a binomial, an NPQ problem? What's more than 5? NP and NQ bigger than 5. If that's true, then it's normal enough. If it's not true, you can't use a normal distribution officially. How are we doing so far? And what's the check for this tweak? So here the check is NP and NQ, each bigger than 5 in order to be able to do this. What's the check for this guy when I take a sample and I have to change the standard deviation? What's true? So before I can do a probability problem here, what do I have to check? I love it. N has to be greater than 30. Okay, how are we doing so far? Is that cool? Sort of. All right. So let's do this. Before I forget, let's talk about the formula sheet first. We can all make our formula sheet. Then I'm going to open it up to whatever you guys want to focus on. You can do some examples out of whatever section you want to look at. So on your formula sheet, take all this stuff away. So what formulas can we have on here? Let me see. So obviously we want this guy. Hopefully some of you guys are like, I don't even have to write that damn thing down. Yeah, shit, I know that stuff. The one thing you have to be careful about is, a lot of you guys draw the picture, and again, that's the formula sheet. This is a different sheet. This is not your formula sheet. Once you draw the picture and you have the mean there, and you guys put this there, you don't, if I got a z-score of 1.72 for this, I haven't told you much. I just drew a picture and told you what I got. Already I can tell I made a mistake somewhere. Because is this above or below the mean?
Below.
So then the z-score should be
Negative.
So either I drew my picture wrong or I got my z-score formula wrong. And normally what we do is we do this in the wrong order. It's always my data point minus the center, minus the mean. Cool? So the most common mistake I see here is this flips, which throws the rest of the problem off and ends up making somebody do something like this, 99.2%. And then I have to say, holy crap, you fit 99.2% in that little thing? No. The picture's supposed to help you. If it doesn't make sense, either you drew the picture wrong, or more likely, you did something like that. You switched those around. You forgot to do 1 minus, maybe somewhere. Or maybe you did 1 minus and you weren't supposed to. How are we doing so far? Yeah.
How do you know when you have to use 1 minus?
I love it. So the chart always tells you the area below. So you do 1 minus whenever you have one of the area above. Yeah, it's almost too simple. But the chart is so single-minded. It only understands areas below. So if we have an area above, or we want an area above, I've got to do the 1 minus thing. Now, all you people that understand the shortcut, you don't have to worry about that. As long as you know when to apply it and when not to.
So anything above the mean needs to be...
No, anything above, period. If I want to know the probability z is greater than negative 1.81, when I look up negative 1.81, I'm going to get that. I got to do 1 minus that to get that side. Cool. And what do you always do when I ask you between two things? Subtract the two areas, right? Cool, I love it. Okay. All right, I've written down one formula, and it took forever to get past that. So there's one formula we can put down there. The next thing, so that's the beginning of, that's actually way back from chapter 3, but we really started using it in chapter 6. I've got, oh, now let me think. Oh, yeah, okay, cool. Let's take a step back here. We definitely want this here. Right, we want those two. That's chapter 5, the first part of chapter 5. And then we have the last part of chapter 5, where we first started talking about the binomial stuff. That was the two most awesome little formulas. Okay. So that pretty much is chapter 5 right there. And then we get into chapter 6 with the z-score, the basic z-score idea. We have the backwards. This is the reason that none of you should miss that question when I say, what does the z-score tell you? The z-score tells you how many standard deviations from the mean to a data point. All right, so you can read that in English and it tells you the answer to the question. There's a gimme. See if first time ever I get 100% of that question, I'm hoping. So there's the straight up z-score formula. There's the backwards one. When we know the z-score, when we want to figure out the raw score. And then we start getting into the tweaks. You got that guy. Continuity correction, there's no formula for it. So unfortunately, you cannot write that down. You just have to know how to do it. Yes, sir?
For the X one, is it X equals 9 plus your z-score times your standard deviation?
Yeah, the mean of the problem plus the z-score that you found or that you need to use times the standard deviation. Yeah.
Okay.
Cool. So it's really just this formula solve for x. Yeah. Cool. All right, and then I think that's it for chapter 5, chapter 6, and then chapter 7. We only have one section, section 7.3, and that was this formula. It really comes off of this guy. You got that formula there. If I ever ask you to find a confidence interval, you know you want a formula with plus or minus in it. Because an interval is from something to something. Right? So there's a gimme right there. I can eliminate all these other stuff. I know I want something with a plus or minus. And we only have one. We're going to have 3 at the end of chapter 7. But we currently only have one formula for that. And then there's the other formula that goes along with this. How big of a sample do you need? Yeah, there's the square root. Z squared, sigma squared over E squared. What's that E? Error. How much you want to be off by. So the within, that's a key word. Would it be within 3 pounds? Then my E is 3. Okay, cool. I'm always thinking about something like at a fair. If you go there, there's somebody there to guess your weight. If they guessed within 3 pounds of your actual weight, that'd be pretty impressive. So you naturally give them an error tolerance. We do that all the time. If you're within this much, I'm like, whoa. You guys kind of... All right. Anybody have any suggestions as to anything else that should be up here? Anything I might have missed? Okay. You guys doing okay? Yeah? Y'all look a little... I'm sorry. I'm not helping all the other problems in your life, I understand. But you're in this class for some reason, and I'm trying to help you with that. Okay, so now let's try some examples out. Anybody have a specific problem they want to start with, or should I just start going to town? Yeah.
Do you want from the practice test?
Yeah.
Can you do number 8 from the practice test that you gave us?
Number 8?
Yeah.
Hello. This is number 8 from the practice test. Yeah. So it tells you a sample of 32. Okay, cool. So N is 32. The mean time spent is 6.1 hours a week. Now, the biggest mistake people make when they start writing this stuff down is they use the wrong symbol and it throws them off. Why did I use that symbol for 6.1? It's sample. I don't use a mu. It came from a sample, so it's got to be X bar. And then what symbol do I use for the 2.25? Be more specific. There's 2 standard deviation symbols. Which one? Now, where's 2.25 coming from? Population. So it's got to be sigma. Now, I mean, we're a little, without section 7.4, we're definitely not there yet. But in section 7.4, we're gonna learn what to do when we don't know this. And if we don't know this, it should kind of make sense that we've got to be more conservative. If I'm not sure what that is, then I've got to use S. But S is more than likely wrong. You kind of with me? So if I'm like, that guy said there's a certain fish here, but he's not really sure, so I'm going to cast out a little bit bigger net than what I think, just to cover myself. Because I'm not really sure about how wide that fish normally swims. So let me just cover a bigger net. That's going to be section 7.4. Here, we have to be given sigma so far, because we don't know what to do with it if we're just given S. Okay, so we got everything identified correctly. They want a 98% confidence interval. So what can I get from that I need? What does that tell me?
Z-score?
The Z-score. So I know how far I've got to go out to catch 98% of the stuff. So I'll be that confident that I caught the right thing. So what's the Z? We actually did 98% before. But just to show you how to do it in general, if I want 0.98%, 0.98 in there, what percentage is outside? 0.02. And what was that symbol for 0.02? That area outside. What's the symbol for that? Alpha. And that's why, alpha looks like a fish. So it kind of goes along with the whole net and fish idea. So outside would be 0.02. So what's just on this side? 0.01. And if you look up 0.01 in the chart as an area, you should get 233, negative 233. Is that cool? So if I ask for a 97% confidence interval, which I will do something like that, then you know how to get what the Z-score has to be for that. Okay. So now I know Z is 2.33. I don't worry about the plus and minus because that's built in to the formula. So they ask me for a confidence interval. Looking at my formula sheet, I know I want to use this dude. That's what I'm just going to make an interval. So now I've got all the pieces parts that I need for this thing. I know X bar, 6.1. Give or take. Z is 2.33. And this part of the formula is because I've taken a sample and I'm talking about the mean. So I've got to change the standard deviation. It used to be 2.25. Now I divide that by the square root of 32. So ever since we've been doing stuff like finding the max and min usual value, you've actually sort of been doing this. You took the mean and you added so much to it, you subtracted so much from it. In fact, on the first test, I had you guys doing something like that. We've been doing something like that for this whole class just about. Now we've come to a very specific use of that idea. And my suggestion is to first figure out what the heck that is. Oh, I can cheat. Let's see if I'm right on that answer key. Where do you guys get? Anybody do that part, the error? Like, I will wait, Jeff. I'm sure you will just tell us, or somebody else will do it. Ooh. So what do you guys get for that? Anybody?
0.9267.
I like it. So we'll say about 0.93. So now all you got to do is add 0.93 to 6.1 and subtract 0.93 from 6.1. Not too bad. Yes, ma'am.
So in this situation, you actually use the Z just as a number instead of an area?
Z is always just a number. It leads to an area. So I don't have to look up the area here because the area is actually this. So the area led me to a Z-score. It's sort of like a percentile problem in a way then. They give me an area, I look up its corresponding Z-score, and then I change it to a raw score. So it's really almost the same problem. I just got this freakiness here because I have to take a sample, and I've got X bar instead of mu because I don't know what the hell mu is. Hopeful. And then whatever the hell this is, let's see. 5.17? You can do it, Jeff. 5.97?
It was 1/7.
1.7.
17?
Yeah.
Thank you.
So
To
7.03.
7.03. So how do you write the little conclusion at the end? What can I say there at the end now? What does that mean?
It's an interval.
That's an interval. I love it. So what does it mean? What is it we're actually trying to get a feel for in this problem? Yeah. So I'm trying to get some feel for it. I know what the sample mean is. I talked to 32 people and I know what the sample mean is. I'm trying to get a feel then for what the actual population mean is without me having to go talk to everybody in the world. Right? So I take what I know and I figure out a range of values that population mean could sit in. So I say, how confident am I that this interval actually catches it? That net I threw out actually catches the fish. This interval that I set up, how confident am I that I caught the real mean? 90%. So we say we are 98% confident that this interval, 5.17 to 7.03 hours, contains the true mean time spent studying. Where do we go? By stat students. Or spent on homework. 5.7 to 7.03 hours contains the true mean time spent on homework. Now, I know as a student, you always just want to know, how do I do this kind of problem? Just show me the steps involved, dear God. But statistics, you almost can't do it without understanding why you're doing what you're doing. And if you understand why this thing works this way, then it makes it so much easier to do it. You kind of know why the hell you're doing it. It makes sense. If you do something silly, you'll catch it easier if you understand what's going on. So I know that the sample mean should be right in the middle. Sometimes I'll get somebody tell me it's like from 3 to 5. That doesn't make any damn sense. You got 6.1. That should be right in the middle. Right? That's a quick check you can do. And the whole idea is, whatever interval we each make, you can make a different interval because you talk to 32 different people and you talk to 32 other people. You each make a different interval, but each time there's a 90% chance that your interval caught the real mean, 90% chance that your interval caught the real mean. So what percentage of all of us, if we each did this, what percentage of all of our intervals would not catch it? 2%. Only 2% of our intervals. So if there are 50 people in here, then I would expect on average one of us to have an interval that actually doesn't catch it. So do I trust this? Hell yeah, man. There's only 2% chance that we're all wrong. Or that at least one of us is wrong. You kind of with me here? A little bit. Okay. Let chapter 7, the ideas are pretty simple. The work is pretty simple. Plug and chug stuff here going on. So normally we can kind of chew our way in it. We can really get our teeth into this a lot easier than some of the other stuff in statistics. So everybody got this here? Formula sheet stuff? Okay. Any other questions specifically from practice tests or from homework? Oh yeah, 8B. Yeah, cool. So there's 8A. 8B. So real quick, to be 98% confident that I'm within 0.93, I had to take 32 people. So if I now want to be within half an hour, not within 0.93, not within, this is almost a full hour, right? This is 0.9 hours. I want to be now 0.5 hours. Should it take more or less people? Should that require more or less people to narrow my confidence interval down? More people. The more people I take, the less I have to kind of go out from it to catch enough. I'm more and more and more certain about what I see then. So that's what this question really is all about. What if you don't want, 0.93 is no good? How many more people do I have to do to talk to get within half an hour? So everything's still the same. The mean is still, not the mu, but the x bar is still 6.1, but that's not even useful here. The standard deviation is still 2.25. What else do we know? The z-score is still 2.33. But now what I need to know then is what's the n? And there's still one last thing, of course, that I know. What's that 1/2 good for? E. I love it. That's how much I want to be off by at most. That's my error. So I want E to be 1/2. So anytime you see a question in the homework or on the test that says how many people would you need to do this or how many things would you need to look at, that's an n equals problem. I want us to figure out what n is. Sigma. So again, now you just plug and chug. So I will never ever teach statistics straight up as a plug and chug class because the concepts are so damn important. But after you suffer through my concepts, if you can at least get a little bit out of it, you can start to look at it as a plug and chug problem. This is now identifying which formula I want to use, what is it that I know from the problem, and then plug and chug. So n is z squared times sigma squared over e squared. What do you guys get for that? When you do that? 109.94. 109.94. So then what do you always have to do, no matter what? Round up. Period. Right. You got to have at least that many. So 109 is not enough. You got to go to 110.
I got 140 something.
Neither. I don't know why. So 2.25.
Oh, okay.
Yeah. Cool. So if I ask you now, I wouldn't actually take any points off of this. Do you need a copy of that? Practice test. I mean, need your what's your name? Okay. You already got that, right?
Yeah.
Practice test. Cool. I've been given that. I have. Yeah. If I asked it this way, if I said, how many more people would you need to talk to be within half an hour? What one little thing do you have to do? Subtract what?
32.
You already talked to 32 people. If you need 110 total, you just subtract to see how many more you need. So this is what I meant as a feasibility study. You do a little bit of a study first to get a feel for things, and then you say, no, that's not good enough. I actually want to be within this much. And then you can see how many more people you need to talk to. In this case, it's only 78 more people. That's not too bad. If I already talked to 32, I could probably get 78 more. If it turned out to be 8,000 more people, that might be a bit of a challenge, right? Oh, yeah.
So the answer to that would be 78.
78 more. I can't remember how I said it here. Yeah, how many more students would you need to survey? So you have to do that subtraction. If you don't do the subtraction, I'm normally pretty nice. I don't take any points off. I just say, because it is not quite a trick question, but you got to do something with the answer you get from the equation. It shouldn't be that big of a step, though, to take. Yeah?
Why is it something?
Because in part A, I already talked to 32 people. So if I say how many more do you need to talk to, and this problem, you do this problem, it says you need 110 total to be within half an hour. I've already talked to 32 people, so how many more do I need to talk to? 78 more to make the 110. Now if I talk to 80 more, I'm definitely going to be within a half. I'm even going to be a little bit better than that at 98% confidence. So two things kind of control how big an interval is. If you want to be more confident, it gets bigger, or less confident, it gets smaller. Are you with me? If you're like, I only need to be 70% confident, then you only have to go out a little bit. Does that make sense? Because you're leaving more stuff out, so that's where the doubt comes in. You're 30% doubtful that you caught it because you left 30% out. You come in too far. Your sample size also affects it. The larger the sample you take, the more confident you are in the first place. You don't have to go far out from it. The smaller the sample, oh shit, you better cover your ass and go further out. Okay? No. So if I take a larger sample, I'm already confident about what I see. I don't have to go that far out to catch the real mean then. I'm really confident it's pretty close. Smaller sample, I'm not that sure about it. I got to go further out to say that I can catch the real mean, to cover my butt for the fact that I got such a small sample. Cool. All right. And you can see that in the formula itself, because if z gets bigger, the error gets bigger. So if I want to be more confident that z-score gets bigger, the error gets bigger, I go further out. If I take a smaller and smaller sample size, divide by small gets big, that would make my confidence interval bigger. So those two things kind of do that. Yeah.
After you have your N and your part B, you subtract the 110 minus what number?
32. So again, part A, how many people did we talk to? 32. Part B says I need 110 total to get within half an hour. I've already talked to 32 people, so how many more do I need to talk to? 110 minus 32. Yeah. Any other specific questions from? Yes.
Number 7 on the practice test.
Yeah, number 7, I'll tell you this. Oh, it's good. 7 is the box plot one, right? Number 6 is the one I got to talk about a little bit. So what do you need? Now we're going to take a giant step back to the beginning. Remember, this test is going to involve section 3.4 also from a million years ago. Oh yeah. So what do I need to make a box plot? What numbers do I need? What physically, what do I need? What types of things to create a box plot? What does a box plot look like? In fact, I like it better when you call it box and whisker, just because it looks a little, it brings up a picture in your head that looks more like what it really does look like. It's a box with freaking whiskers on it. Right? It's like my attempt at a cat. Just put some eyes above that and there you go. I'm really horrible at art. So box and whisker, it should look like this somehow. So I need 1, 2, 3, and then let's put that in 4, 5 numbers. Right, that very middle line that I just added in there, that's going to be the middle of all the data points. That should be the median. Careful, not the mean in this case. The median. The mean, does it have to be right in the middle of the data? No, doesn't have to be. Right? I can have all these small numbers and then some crazy big-ass numbers. My mean is suddenly way up here. But my median doesn't care. My median will always be right in the middle. So what do you call those numbers, those 5 numbers? 5-number summary. I love it. And the 5-number summary, what are they? That's probably the lowest. Good. Low, high, I bet it was on the other end. And what's the 3 in the middle? We already know the one right in the middle is the median, which is also known as Q2 or P50, right? So Q2, that's the median. So of course, what do I need on either side of that? Q1 and Q3. Beautiful. Right? And remember, when you do 1-bar stats, this is the last 5 things that's in the list. That does not mean that counts as your work. Do not write down what buttons you pressed. But it's a good way to check your work. So Q1, Q3. So, I mean, the low and the high, easy. Just put your list in there and sort it. You can figure out the low and the high. How do I get Q1, for example? In fact, somebody help me out. What's the sample size in this problem? Number 7. Yeah, what's n in this problem? 16. There's 16 numbers there. So how do I specifically find where Q1 is in that list. What do? What's the first step? If I have a group of 16 numbers and I want the 25th percentile, I want to go in 1/4 of the way. I take 16 and I do what to it? I want to go 1/4 of the way in. So how far is that? If the whole trip from here to wherever I'm going is 400 miles, and the first day I want to go 1/4 of the way, how far do I want to go the first day? 100 freaking miles, right? So 1/4 of 400. Of course, in general, 1/4 is 25%. So you take 2.25%, 25%, 0.25 of 16. And of course, 1/4 of 16 is 4. And whenever you come out with a whole number, what do you do with that? I love it. So if it comes out to a whole number, you take the average of that with the next. So that's the 4th number and the 5th number and average them, right? So this will be the 4th and 5th averaged. If I came out to 4.07, the 5th number, you always round up. So if it comes out to a whole number, you average that with the next one. If it comes out to anything else, you round it up and take that one. So my answer for Q1 will be the average of the 4th and 5th number when these are in order. So obviously the first step on this kind of problem is put the list in order. Okay. And then all you got to do is go find the 4th and 5th one and average them. Not a problem. Is that cool?
Yeah.
Do the same thing for Q2. Q2 is a median. We have other ways to do that one because it's a special case. It's like right symmetrically in the middle. Q3, I just take 3/4 of 16. I want 75% of the way in. Some of you guys might remember the shortcut. If this was the 4th and the 4 steps in, this one's going to be 4 steps from the end. Or you can just do 75% of 16 straight up, right? How are we doing there? Is that all right? So first step, put it in the list and sort that bad boy so that you can find these things. So let me do this. Let me go ahead and give you guys the answer key. 2 things about the answer key I got to tell you. Let me give it to you first. Make sure you got a front and back. Everybody's far away from you. Sure. Okay, so real quick. Here's the 2 things. First off, you'll notice, starting at number 5, I changed number 5 to number 7 on here, so your numbering just a little off on the answer key. I have faith in your ability to match up the problems with me. So number 7 on the answer key actually references number 6 on the practice test. Yes, ma'am. Oh, one more. Can you pass it? Secondly, my number 7, I had changed it a while back, and I think I used an old copy of my practice test. I'd rather use the numbers on the number 7 on the answer key. It's more true to life of what I give you. So if you tried out number 6 on the practice test already, that was a little bit harder than what you're probably going to see on the test. If you did okay with that, then you should be okay with what you'll actually see. If you look at number 7, I changed the numbers around just a little tiny bit. Right? And it actually makes it a bit easier to beat. Okay. So be careful about that. Put a note to yourself. So you're not looking at this and going, holy, I didn't get that at all. Well, because I changed the numbers in the answer key. Okay. Is that all right? Okay, so I'll let you guys look through that for a minute.
You know how you said you'll give an example on every test, or excuse me, a section on every test that asks what the z-score means? Would you do a problem, or?
There's only 2 ways I could really ask that question. I can ask you directly like I did on the first test. Yeah. What does the z-score tell you? So what does the z-score tell you?
How far away from the average you are.
Alright, that captures the idea, but then I'm going to be a real dork, just to tell you. I'm going to say, what, in light years, in miles, right? Because how far away, just saying that by itself is not good enough. You say it's 7 away.
The distance
7.
away.
In what units? In centimeters? In furlongs? In fathoms? Parsecs, if you want to talk about, what is it, Star Wars? Anyway. Some of you guys get that reference already. Some fellow with true beats. What was Harrison Ford talking about? If you don't have a clue what the hell I just said, z-scores are always measured in standard deviations. Okay? So the z-score is the number of standard deviations from the mean to a data point. That's it. I always get some interesting combination of those words that don't make any sense grammatically. So don't just think if you get all the words down, it'll work. All right, it's not definition soup here. You got to actually get them in the right order, so it makes sense. However else you want to say that yourself, if it makes sense, if it's actually the truth, if you have a different way to say it, I love it. I'd much rather you understand it than just memorize a statement. But if I can get that out of you, I would feel really good. Most of you guys normally get that right because it's not that big of a deal. The only other way I could do that, the only other way I can really ask the question is I could be more specific. I can say, what would negative 1.87 mean as a z-score about a data point? So if I got negative 1.87 as a z-score, what would that tell me about the data point? Negative 1.87. What does that tell me about that data point? It's below the mean, how far?
By 1.87, negative 1.
By 1.87?
1.7
Standard deviations, 11. So you could say it's 1.87 standard deviations below the mean. You know it's below because it's negative? And 1.87 is the number of standard deviations from the mean to the data. So I can ask you either directly or I can ask you more specifically, give you an actual number. Those are the only two ways I can ask you that question, yeah. Is that cool? Now if you say away from the mean, not above or below, that's fine. But if you say above or below, I'll be a little tear of it. That's awesome. I actually will. It happens. Any other specific questions, or is there a kind of problem you want to look at? Like a NAB problem, maybe, or yeah.
Can we look at 5? I don't really, doesn't matter which one.
Let's look at one of the answer key. Because again, I'll focus on that one. Wait. 5 is the one.
Oh, no.
The one about the California school students and all that? Yeah, okay. Let's see, so in a recent year, grade 8, blah, 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 blah. They had a mean of 281. And why do I use that symbol for that? Yeah, why do I use that symbol, mu? Populations, all of them. I didn't say a subset of them. I didn't say 20 of them. I said grade 8 California school students. There you go, all of them. So the mean of that population was 281. Standard deviation is 34.4. And I'm assuming that they're normally distributed. And then I proceed. And this is a beautiful example of section 6465. That kind of idea, because I'm going to start off with picking one student, and then I'm going to start picking a group of students. Right? So part A is, if we pick one student, what's the probability that their score is higher than 315? Pick one student. And this should be the problem where you're like, please, Jeff, put a ton of those on there. If you don't quite feel that way, you want to get there. Trust me. the more comfortable you are with this kind of problem, the better you are with two main types of problems, the NAB and the central limit theorem, when you have to change standard deviation. If you're not comfortable with this problem, then how can you be comfortable with tweaking this problem? Don't come in. Somebody's really making a point. So what's the steps here? What's the first step? What's a really good first step? Make it happen. Draw a picture. I love it. And again, a lot of you guys don't draw the picture, and you're the ones that make the mistakes normally. You give me an answer that's not right because you didn't realize you had to do 1 minus or something. Right? So what goes right in the middle? 281. Where's 315? Over here. Right? It's bigger than 281. And I want the area where? Where will I shade? Above. I want greater than, so I want that area there. So already I know that it's not going to be, it's going to be smaller than 50%. My scale I'm not sure about. And I don't care about it. I just know that my answer should be smaller than 50%. Cool. So what's my next step now after I draw my little picture? They gave me an X score, so I want to make it into a Z score because then I can look up the area, which is the probability. So how do I make that into a Z score? Good, 315. My data point minus the mean divided by the standard deviation, which is still this, because I'm only talking about one person, and that's what this is good for. Individuals. So 34.4. .99. Of course, how did I do? All right, so that's the Z-score. Now this is where you got to be careful. This is where I get a lot of people say 1 minus 0.99, and some of the answer is 1%. But you're telling yourself that is a Z-score mean. So that's going to be right here, 0.99. So I have to look that up. How do you guys like the shortcut that I showed you? Anybody use that? You guys? Okay, cool. So I'm never going to show that in class, just to let you know. I'm going to always show it the full way. So if I look up 0.99, can somebody help me out? What do you get when you look up 0.99?
0.8399.
Yeah, so I look at 0.99, I get 0.8389. I like it. How are we doing so far? Is that all right? Is everybody cool with that? I can put that up here. Let me do that. Let's see a few concerned faces. Or faces of concerned people. I guess your face can't really be concerned. This is why I teach math. Yes.
Can we use our Z-score sheet on the test?
Oh, hell yeah. And I will be collecting your Z-score sheet with the test, so do not write anything on there. If you have written anything on there, you want to get a clean sheet. You want to have a clean sheet to use for the test. You can put your name on there if you really want to. But if I see anything scribbled or erased or anything, that's not good. That's notes. You can't have notes on there. Yeah.
How do you know if you find like the?
Here you go.
I don't like in here or out here.
Oh, I got you. What is this? What is it? It's a Z-score. So then I look out, see here where it says the Z's are out here? So then I know I can look out here. When do I look in here is when they give me a probability or an area. If they say, what person would be in the top 5%? Okay, 5% is an area. I would look at 0.05 in here, right? Or actually in that case 0.95. We won't get into it. So that's, you look up here when you know it's an area. You look out here when you know it's a Z-score. I know that's a Z-score because I just calculated it. So I get 0.99. So there's my 0.8389. Cool. And so how do I get the actual answer for this question then?
1 minus.
Yeah, 1 minus 0.8389. 1611. Just over 16%, if you want to write like that. See 16.11%. Yes, ma'am.
Oh, sorry.
Yes, sir.
Part B, do we have to find the sample mean, or, let's find the sample mean, or no?
Oh, okay, good. So part B, there's a part 2 to this part A, right? But I think maybe it'll be okay to go past this. This is part 1. There's a part 2 where it says find the probability between these two, but you just make them both into z-scores. You look up the areas, you subtract them. Is that cool? So part B says if we take, Jeff, there you go, 2,000 students. How many would be expected to have a greater than 315? How many expected?
Expected value is the mean.
Exactly. Right? So the expected value here. The minute I say that, though, I think we all kind of go to weird places. We're like, X P of that? No. What do I have here? I have N. And what do I have in relation to 315 that we've calculated? P. I've got a probability. So what's the mean in that case? NP. Because what does this really mean? Any individual student has a 16% chance, but actually it makes more sense if I say just over 16% of all those students would have made higher than 315. So if I take 2,000 students randomly, how many would I expect to have higher than 315? 16.11% of them. That's what that means. And that's why that mean NP makes sense. Percentage of the number. PN. Percentage of the number. So in this case, the expected value would be the mean 2,000 N times P 0.1611. Which I forget. 30 something. 300 something. About 322. So I just truly rounded that one. It's about how many would you expect to see. It's not how many do you need to do something. Is that cool? That just shows you that mean is NP. You can use that in more places than somebody just giving you a P. We figured out what P is. What's the probability of somebody getting greater than 315? 0.1611. So now if I take 2,000 people and I say how many would you expect greater than 315? NP. I just calculated my people. Who cares where it came from? I can use it the same way. And then what happens when part C is what kind of problem? 5C. That's one I was just talking about a minute ago. What do I give you? What is that 5%? Where would that be in the picture? What I put down here somewhere, 0.05? Probably not. Normally it's not where I start. Not the first example. So what's up 0.05? What is that 5% physically in the picture?
94%.
In the area. And I want the top 5%. So there's 0.05 right there. So then what kind of problem is this? They want to know what score. The scores are the X's, right? Anytime the 315 was an X. Now they're asking me, what's X? What's the score, the test score? What's the X for a given percentage? It's the exact opposite of this problem. They gave me percentage where here I had a percentage at the end. So what's the next step? Where can I go directly from a percentage? What can I look up? Yeah, I want to find the z-score. So if I don't know the shortcut, don't like it, I have to look up that area. Because the chart only understands the area below. So what's the area below in this case? Yeah, 95%. So if you look up 0.95, the closest I can get to 0.95 is right in between these two. So if I follow the asterisk down, 1.645. By the way, while I'm looking at this, you guys notice this is what I call the baby chart? The little baby chart. If you want to be 90% confident, you use this z-score. If you want to be 95%, use that z-score. Do you guys see that? Yeah, Jeff, you're showing it to us. All right, good point. But that's really nice. I mean, it doesn't have 98%, it doesn't have 97%, but it does have the three biggies. 95 is the most common one. But these three of them are the biggest ones used in general. Gallup almost always uses 95% confidence intervals. So if you look up 0.95, I get 1.645. How do I change that back into an X score? How do I change it back into a test score? Yeah, X equals. I want to know what X is. So now I just plug in shut. Okay. I know the mean is 281. Got it. I know my z-score is 1.645. Standard deviation was 34.4. Cool. Now I just plug in shut. That's directly applying the idea of z-score. If I want to go to 1.645 steps away, well, I multiply that by how big each step is, and I go that far away. And the biggest mistake I see on Part D is I get exactly this work back again. And I get the same answer. So when somebody looks at Part D, they'll do this. What mistake did they make? Yeah, what has to change for Part D considering what's going on in Part D? Yeah, Part D says if we select 33 students and then all the questions I'm asking are for X bar, they're all about the mean. So I took a sample, I'm asking about the means, I've got to change the standard deviation. So for Part D, the only thing that changes in this whole thing is that number there. I can't use that standard deviation because what's that standard deviation for? What's this one good for? Individuals. What I need now is a standard deviation for samples. So the only change for Part D, where can I put this? Part D, the first thing I've got to do is change the standard deviation. It used to be 34.4. Now I divide that by the square root of, what was it, 33? Because I took 33 students. So notice, I'm glad you kind of said that, Tyler, because the biggest mistake people make is they think that I'm changing this into a sample standard. I'm not. It's still a population standard deviation, isn't it? It's the population of all the sample means, all the possible sample means. They will have a standard deviation of this. Whatever the hell that is. So it's beautiful. That's why if you understand this better, all Part D is do the same damn thing, but instead of dividing by 34.4, divide by whatever that is. 5.99? 5.99? Cool. What did I use? 5.988. I don't remember what the fourth number was, but I won't. Ah, there you go. So 5.988. So it's the same exact work. You just don't use that number because that number is for individuals. I need the one that tells me how spread out groups of 33 are. That's what that number is. So the z-score, picture's the same. The z-score will now be 315 minus 281 divided by this now. It's Morse code. Somebody's in trouble.
How far do we round it?
Which part?
Well, the answer. Just a 3 space.
Like your percentages, you can always take to 4 decimal places for the decimal, right? Because that's what's going to come out of the chart. Z-scores, of course, are always just 2 places because the chart only goes out to 2 places. Is that cool? So those two are kind of nice and set. Probabilities, you can take out to 4 because that's how far that goes. Z-scores, you take out to 2 because that's how far that goes. We're kind of constrained by what we use. Once we're actually, the funny thing is you'll love this. Once we're done with this test, I'll show you the shortcut in the calculator for how to do this whole problem in 1 step. I will not show you now.
And we're gonna
Huh?
love it if we wasted all this time.
That is such the wrong word to use. I mean, I hopefully some of you guys understand why we do these kind of things. Why do all your math teachers, hopefully all your math teachers, make you do so much by hand that technology can do? If you've ever looked at Wolfram Alpha, there would be no reason for humans to get up out of bed if we wanted to go that way. Wolfram will do it for me. Then we'll all be like those humans in freaking Wall-E, right? That's sad to me. So I force you to do a lot by hand. I force you to use the chart. You know why? Just so you get used to how things are kind of spread out in the picture. So you really see where those numbers are coming from. The graphic calculator will give me numbers. It'll give me better numbers. It'll give me more precise numbers. I don't give a shit. I'd much rather you kind of absorb the idea. That's so much more important than getting the exact answer. This only goes out 4 places. Who cares? It's good enough for the idea. I don't know if you ever noticed, that's why in the back of the book, Trail always has a technology answer. Have you guys ever looked up your answers in the back of the book? They always have this, technology, this. It's always a little bit different. Whoop-de-doo for technology. We can do this stuff by hand. We can get the idea. All right, is that cool? Of course, you guys can see on the answer key where I finished that out. It's the same stuff as this, just using the right number, yeah. About 0%, yeah, because the z-score I got was 5.68. If I rounded to a couple places. Is that on the chart? So if you say instead, if you look up 5.68, and you can't, so what's it say here? The best it says is 0.9999 for everything past 3.5. I have a big problem with that because 3.51, 3.52, 3.53, they're always getting a little bit bigger than this, a little bit bigger than this, a little bit bigger than this. So once I'm out to freaking 5.68, I am a decent amount bigger than this. So if, and my picture here is going to be the same as up here, if below here is about 1, above here is about 0. Or even better, I could say like the 0 plus, remember that symbol? It's saying it's not impossible, but it's pretty damn unlikely. That's exactly what I mean there. It's not impossible, but it's pretty damn unlikely. Because almost 100% of the information is going to be below that. We knew that from empirical rule. Empirical rule says you go out 3 steps, you catch almost every damn thing. Now I'm talking about going out 5.68 steps. Well, shit, that's definitely just about everything. Maybe it leaves something in the 14th decimal place. Okay, maybe. So it's important that you know the answer is not 0, but it's so damn close to 0 that we say, okay, it's basically really close to 0. It's almost impossible.
So if we put 5.678, we get it wrong?
No, well that's the z-score, so he has to give me a probability answer. Yeah. So I have to see something. So if you put down there 0.0001, because you did 1 minus this, I'm going to take it. That's fine. I'm going to take it. But I really want you to realize about 0 is even better. It's more precise, actually. More truthful, let me say it like that. Yeah?
Why is it not 0.999?
Oh, because the question is above. So that's 0.999 below, right? It always does. So I have to do 1 minus that. So if you do 1, you get 0.0001, which I'll accept, but it's even smaller than that.
How do we know that it's smaller than that?
Because I'm even past 3. If I'm right at 3.5, then that's the right answer. I'm way past 3.5. So that can't be the right answer anymore. That's one thing I don't like about this, is they make it sound like it's always this. No. Okay. Any other questions on anything? Okay. Yeah. Oh, number 6. Yeah, nobody really asked me about this one directly. This is the one I thought I'd get all the questions on. The one about the DNA, right? So this is the one I want to look at the practice test. I changed the numbers up a little bit, but the idea doesn't change. So number 6 is number 7 on the answer key. I tell you that 93%, so P is 0.93, thought that DNA tests were very reliable. We selected, number 1, we select 24 people, so N is 24. And I ask you, what's the probability that exactly 23 of them? So how do I set up that formula for it? The probability exactly 23. How does that formula get set up? And which formula are we using? What kind of problem is this? How many outcomes are there? No? Huh? Not a lot. Either you think it's reliable, very reliable, or you don't. There are 2 outcomes, right? I can roll a dice. I can roll a die and have 2 outcomes. It's 5 or it's not a 5. If I'm playing Yahtzee and I need my 5s, that's my world, right? If any of you guys know what Yahtzee is, maybe you don't. I don't know. No. So if X is 23, this is the whole problem. This is the NPQ problem. I keep calling it like an NPQ problem. NPQ problem. This is where you use N choose X, that whole thing. Right, it's built off of how many P's and how many Q's do you have. So if I want 23 successes, well, what's Q first off?
7.
Yeah, 07. Sometimes I get somebody tell me it's 0.7 or something. You gotta be careful. That's going to throw you off. So if I want this probability, I got 24. I want to choose 23 to succeed. So how many successes do I have? 23. And how many failures do I have? 1. And just toss that into the calculator. And where do you get that C from? Math. PRB. And then I think it's number 3 or 4, I can remember. It says NCR. So that's where you get the C. So you put 24, math, PRB, NCR. 23 times this to that, times this to that. Okay.
And that's raised to 23.
Yeah, raised to the 23rd power. I always have a problem with 3s. Part B now is sort of like the opposite of the kind of problem I would give you when I say at least 1. Part B says, what's the probability that X is at least 23? Well, what's the only thing that not at least, but at most. What's the only thing that at most 23 leaves out? 24. So there's only 24 people, right? So anytime the opposite probability involves less work, I will do that. Right? That kind of makes sense. So this will be 1 minus the opposite. So you do the same thing we just did, but now you do the probability for 24 instead of 23. And then you subtract it from 1. So it's not anything to do with at least 1 specifically. That's just a very common example. Anytime the opposite probability situation is easier, of course I'm going to do that, because I just got to do 1 minus that. Anytime. And then part 2 is where we get into the NAV. And that's pretty much exactly how I have it set up. Find the mean and standard deviation, check in P and NQ, and on the test I might ask you, what does that mean? Sounds like something you want to write down, because that will probably happen, and I just told you that. Gave you something away. What does it mean if you get NP and NQ bigger than 5? It's normal enough. I love it. Or if you just say approximately normal, whatever, beautiful. And now that's what allows you to do part C. Right, so get a z-score to look up the area. But of course the NAV is where you have to do what? Continuity correction. That's right, continuity correction. Go up or down by a half. So when you see that NAV, that's my clue to you. That's me being remarkably nice, because I didn't used to do that actually. Use the NAV. Okay, you know you have to go up or down by a half. Okay, that's plenty, guys. We're actually 5, 6 over. So if you didn't get your quiz back, or you need a copy of the answer key or something, come up and see me.